Hey everyone, thanks for joining us today. Today's IGS seminar is one of the early career talks, so we'll hear from 3 different people for about 15 minutes each, and then there will be one period at the end for questions for all 3 of them. So we'll get into it. Our first speaker is Denis Felikson. Denis is a newly minted research scientist with the University Space Research Association, working in the cryospheric lab at NASA's Goddard Space Flight Center. He works on measuring and modeling changes of the ice sheets and projections of sea level rise over the next century. He's also recently worked on the Ice Sheet Modeling Intercomparison Project, or ISMIP-6, helping to develop a standardized ocean forcing approach there. So today, Denis will talk to us about seasonal tidewater, glacier terminus oscillation bias from multi-decadal projections of ice mass change.
Okay, thank you, Lauren. Huge thanks to the IGS and especially to Katie and Lauren and Rebecca for setting this up. These global seminars are great, and it's nice to be able to speak to all of you, if not in person, at least over our virtual computers. So, as Lauren said, I'm going to give a talk today, a short talk on seasonal oscillations of glacier termini and how that affects long-term projections of ice sheet change, ice mass change. So this is work that I did with Sophie Nowicki, who was my postdoc mentor at NASA Goddard Space Flight Center, as well as Isabel Nayas, Matthew Morligam, and Helene Cerruti. And I wanted to acknowledge that this work was funded by the NASA postdoctoral program. As many of us know, tidewater glaciers are really complex systems. There are a lot of processes that operate at different time scales and different spatial scales that are really difficult to measure and to model. For a lot of these processes, we have parameterizations, but the underlying physics are not necessarily well understood. So it's difficult to predict the behavior of these systems. We also know that tidewater glaciers have been changing pretty rapidly, coincidentally, since we really started tracking them closely with satellites over the last 20 or so years. This is a figure showing Greenland ice sheet thickness change. And if we zoom in on the margins here of the ice sheet, we can see how the tidewater glaciers, the outlet glaciers that bring the ice sheet, have changed over the last few decades. Some of them have changed quite substantially and very rapidly. And because these systems are complex and hard to measure, it also makes them difficult to model, and projections of the future of tidewater glaciers are very uncertain. So when we try to project what will happen over the next 100 years or so, depending on how we tweak the parameters in our models, we get widely different results because these parameters tend to be very uncertain. We also know that lots of tidewater glaciers are very sensitive to the position of their terminus. So as terminus retreat happens, most tidewater glaciers undergo acceleration and dynamic thinning in response to that terminus retreat. And there have been some studies that have shown this pretty well for outlet glaciers around Greenland. Here I'm showing one study that modeled the evolution of Jakobshavn Isbrae, which is a huge outlet glacier on Greenland's west coast. And this study showed that in response to terminus retreat alone in the model, the velocity, the speed up, the acceleration that occurred pretty closely matches what we observed to occur on this glacier. So lots of tidewater glacier systems are very responsive to what happens at their front, their calving fronts. But terminus motion variation happens at a lot of different timescales. So here I'm showing a plot from a paper by Ginny Catania that took a very close look at tidewater glaciers on Greenland's west coast and showed that not only do they undergo kind of decadal or multi-year retreat that happens over spatial scale of kilometers, there's also much finer, higher temporal resolution motion that happens in the terminus that happens on smaller spatial scales, but at much higher frequency. And what a lot of modeling studies do, for example, this is the approach that the ISMIP-6 project took, is to simulate or to force ice sheet models with this longer term, multi-year terminus retreat and ignore, for simplicity, the higher frequency motion that happens on seasonal or even finer timescales. And so the question that I'm interested in looking into here is, are these high frequency terminus motion, are they important to longer term projections of the state of a glacier or of an ice sheet? So to address this, I'm going to present this one experiment that we've done using an idealized setup in a model. So we using the ice sheet system model, ISSM, which is a 3D higher order numerical ice flow model, we set up an idealized tidewater glacier geometry. So we modeled this based on the 3D MISMIP bed geometry, but we changed it slightly because MISMIP was more focused on Antarctic ice streams. And so here we're trying to focus more on Greenland outlet glaciers and more generally tidewater glaciers. So we slightly changed the geometry by doing things like steepening the fjord walls and creating this over deepening. And we set this up to first to create a steady state glacier. So we grow our glacier to steady state. And that's kind of our starting point for the simulations that I'm about to show. So here in the top plot, what I'm showing is a flow line profile of the glacier as it starts in steady state. You can actually see that we did this for two glaciers. We have two initial starting points, one where the terminus sits right basically on top or maybe a little bit downstream of this sill or this high point in the bed, this bed bump, and another where the terminus is sitting just behind that. Here I'm showing in map view the bed topography. Ice flow is from left to right. It's going to be from left to right here, and here's the speed, the initial speed. So this is our glacier in steady state, and I'm going to claim that this is kind of typical of a tidewater glacier. And what we do is we prescribe terminus motion of this glacier away from the steady state in two different ways. First, we prescribe terminus retreat to this back to this one position that's shown by the dashed red line. And in another simulation, we prescribe seasonal terminus oscillations around this mean dashed position. So the frequency of this seasonal oscillation, the period, it has a period of 1 year, and the terminus position in the dashed line is exactly in between the most retreated and the most advanced positions of the oscillating terminus. So we prescribe this in the model using the level set method. So there's no calving law and there's no kind of parameterization of what is happening in terms of frontal ablation. We're just chopping ice at every time step or letting the glacier advect ice forward as it seasonally advances. Okay, so a first look, here's what we get when in our first simulation, where we just prescribed the retreat to a stationary position. So this is actually a movie that's showing the first 10 years of this simulation. On the left here, you see thickness change. So after we force the glacier to retreat, thinning initiates near the terminus and then diffuses upstream. And the glacier accelerates also. So let me play this movie again. You'll see as the terminus retreats and then it remains parked there, the glacier accelerates to a new faster steady state velocity. Okay, so that is totally expected and all well and good. And now I'll show in a movie what happens when we force the terminus to oscillate with a seasonal frequency. So and I'll play this movie a couple of times. if you watch what's happening here, as the glacier retreats, there's a wave of thinning that initiates and diffuses upstream. And then as it readvances during the second half of each year, that thinning slows down. And it actually, the glacier starts to re-thicken. All of these plots are showing the difference from every model time step from the beginning of the simulation. So this glacier, even though it's oscillating, it remains thinner than its initial steady state because it's oscillating around a more retreated terminus position. And then you can see what's going on with velocity as well. So seasonally, we get this acceleration, and then as we re-advance, we get a deceleration, and it almost decelerates back to its initial steady state velocity. But the interesting thing is what happens when we compare these two, the glacier where the terminus remains parked in one position compared to the glacier where the terminus is oscillating. And so here what I'm showing is I've taken the last year of our simulation. So we run our simulation for 30 years. And at the end, the oscillating glacier has entered kind of a dynamic steady state. So its thickness and velocity are oscillating, but they repeat year after year. So what I'm showing in this plot is the average thickness and velocity of the oscillating glacier minus the thickness and velocity of the non-oscillating glacier. So in that last year, the annual average thickness of the oscillating glacier is thicker than the non-oscillating glacier, and it is slower than the non-oscillating glacier. So on average, over the course of that last year, as the oscillating glacier is in kind of this dynamic steady state, it's thicker and a bit slower than the non-oscillating glacier. And what that means is that when we look at mass change of this glacier, if we look at the annual average mass change, what we find is a bias between the oscillating glacier and the non-oscillating glacier. In other words, the oscillating glacier has lost less mass than the non-oscillating one. And you can see that here in the plot. So what I've drawn is the wiggly line shows the mass change of the oscillating glacier. So every year it goes through a seasonal cycle of mass loss and mass gain. And the lines with the X's show, the darker line with the X's shows the mass change of the non-oscillating glacier. So it retreats, but the terminus remains stationary after that initial retreat. And if we draw the average, the annual mean through the oscillating mass change, we can see that there's an offset between the oscillating and the non-oscillating glacier. What we have also tried in our experiments is two different sliding laws. We have the Budd sliding law, where there's a dependence on effective pressure at the base, and the Weirtman sliding law, or a hard bed sliding law, that doesn't depend on effective pressure. And we find this bias exists in both cases for both sliding laws. We've also tried, as I said in the beginning, we had two initial states for our glacier, one where the terminus was pretty much right on top of a bed bump, and one where it was just behind a bed bump on a retrograde slope. But nevertheless, this bias exists in all of these different cases. So, and I think this is my final slide here. This is kind of a summary slide. The other thing that we tried was changing the magnitude of our seasonal oscillations. So in all of those experiments that I showed you before, those results showed our simulations that had 1.25 kilometers of oscillations. So that's kind of on the high end of what we observe seasonally in tidewater glaciers. When we try smaller magnitudes of seasonal oscillations, not surprisingly, we get smaller offsets, but nevertheless, they're still there unless we go to really small seasonal oscillations. So here in this plot, what I'm showing is the X's show the total mass change from the beginning of the simulation for the non-oscillating glacier, and the filled circles show the annual average mass loss from the beginning to the end of the simulation for the oscillating glacier. So where this dark filled circle and dark X disagree, this is that bias between the oscillating and the non-oscillating glacier that we find. And you can see it exists in all cases, again, as I said, until we get down to really small magnitudes on the order of 600 meters seasonal oscillations. What is interesting here is that we, not only is this bias sensitive to the magnitude of the oscillations themselves, but it seems like it's more sensitive to the bed slope at the front than it is to the particular sliding law that we choose. Now, the whole point of these experiments was to think about whether these higher frequency oscillations need to be accounted for in ice sheet or projections of for sea level rise, numerical projections of ice flow, and we think that this bias indicates that we do need to look a little bit further into including these higher frequency oscillations in, for example, ice sheet model simulations, because this bias exists. The next step, a good next step would be to try this out on real glaciers. So using an idealized setup allowed us to control a lot of unknowns in our model. But it would be really neat to expand this to look at real tidewater glaciers, plugging in their real geometries, and rerunning these kinds of experiments to see how seasonal oscillations affect their long-term mass changes. So I'll end with that and pass it off to Tree, and we'll take questions at the end. Thank you.
Yeah, awesome. Thanks so much, Dennis. If you have questions for Dennis, feel free to put them in the chat or just keep them in mind until the end. So next we have Tree Datta. Tree is a research associate within the Ice Sheets and Climate Group in the Atmospheric and Oceanic Sciences at the University of Colorado Boulder. Her previous postdoc work was within the Cryospheric Sciences Lab at NASA Goddard Space Flight Center. And Tree focuses on surface mass balance processes over ice sheets and ice shelves using global and regional climate models and new observational techniques. So today we've got Tree talking to us about intense surface melt over ice sheets and ice shelves.
Can you hear me?
Yep.
Okay, great, thanks. Okay, so the introduction's over. I'll just start talking. I'm going to be talking about intense surface melt over ice sheets and ice shelves, focusing on two specific examples, one over the Larsen Sea ice shelf and one over Western Greenland. And yeah, so, and this is, by the way, both a combination of my PhD work as well as my last postdoc work. So let's start off by talking about these physical processes themselves and why they're important. If we just sort of consider the top half of this diagram, which is, this is from Peter Kuipers-Munneke in 2014, what we can see going from left to right is the way that fresh snow has all of this pore space which meltwater can filter into. And as that refreezes and densifies and firm, it can eventually hold a melt pond at the surface, like a table. So this meltwater can also filter into pre-existing fractures and widen crevasses, and then eventually lead to hydrofracture on ice shelves. Now, by contrast, or I guess in addition, this is a diagram from Catania et al. 2019, which I really like. And what I want to draw your attention to is the way that on the grounded ice sheet, surface melt can collect in superglacial lakes, and when they drain, be injected directly into the bed. And this can lead to lubrication of the bed and eventually acceleration, thinning, and retreat. So within this talk, I'm going to be focusing on the Larsen Sea ice shelf. And while the total periods being studied is 1979 to 2017, I'll be focusing on one event in winter in 2016. And the atmospheric driver in this case is foehn winds. And this particular event was discussed, I think, first by Kuipers-Munneke et al. 2018, as well as Weisenegger et al. 2018. And I'm primarily going to focus on the firn processes here, mostly because that's what a regional climate model at 7 kilometers lets us do. And the second event is going to be Western Greenland in summer of 2019. And in this case, the atmospheric drivers are reduced snowfall in summer, which produced a melt albedo feedback, whereby you have melt and that lowers the albedo, which enhances melt further, and it cascades into this feedback. And these conditions favored advection of warm, moist air along the western part of the ice sheet. And so this is discussed in Tedesco and Fettweiss et al. 2020, but that's not really, the atmospheric drivers aren't really what I'm focused on here. What I'm focused on is superglacial lakes and how we estimate the meltwater in them. So to start off with foehn winds, this is a really idealized diagram from Elbridge et al. 2015, and for thorough treatment, I'd really recommend looking at that paper. But this is kind of like your classic foehn wind. And if we think about this as the mountain range here would be the Antarctic Peninsula, and on the left side you have circumpolar westerlies coming in, and on the right side you have the Larsen Sea ice shelf. So what this classic foehn effect is that you have this cool moist air which drops moisture on the windward side and then turns into a warm dry foehn wind as it descends adiabatically on the leeward side on the right. Additionally, because of the loss of the moisture on the windward side, you end up with these cloudless conditions here. So you can see these kind of this classic image of the Larsen Sea ice shelf, where on the western side you have all these clouds, on the right you can see a lot of surface melt. So this was mostly covered in this paper here, which came out in 2019. But what the paper primarily did was inferring foehn winds from either surface melt occurrence, like patterns of surface melt occurrence, which are like fingerprints of the atmospheric drivers, or by finding the melt that's associated with atmospheric drivers that are calculated from the regional climate model. So if we look at the left side here, what I'm showing here is and then, this was done with both passive microwave, which is a 25 kilometer resolution, and with the regional climate model MAR. So this is surface melt occurrence, and what patterns do they form? And then from that we can backtrack and find the atmospheric drivers. And so what we found was that in this case, EOF, and this is using the MEF analysis, EOF1 and EOF3 are associated with foehn winds. And this occurs 50% of the time in the case of EOF1, and then 7% of the time in the case of EOF3. So we can see these very distinctive melt patterns, which are, at least according to the climate model, very much associated with foehn winds. Now, this other method, what this did is calculate the onset of foehn winds using a system that was initially developed by Cape et al. And Spears et al. 2013. And I combined this into the foehn index, which is a time series of aerial extent of foehn occurrence. And as we look at this, what this is showing is the amount of total surface melt occurrence or surface melt production, according to the regional climate model MAR, whenever a foehn wind is occurring. And what we can see is that you have this very strong melt event that happened in May of 2016. And this is, going all the way back to 1979, this is the first time this has happened. Sorry. Okay, and we can see this also in observation. So we're seeing here on the left is from Sentinel-1. This is just May 2nd, 2016. And on the right is the total meltwater production in May 2016. And one thing I want to kind of point out is that the way that you can see these sort of tendrils of melt happening in the observations, which aren't entirely captured in the model. And part of this is because the climate model was hydrostatic and at a 7 kilometer resolution, so it didn't perfectly capture eastward flow. But I think the main takeaway for this, and what sort of informed more of my work in the future, was this is what we're looking at here is a time series from left to right. This is going from July 2015 all the way to July 2017. And each of these time slices is the entire, it's essentially collapsing space over the region where foehn winds occur in January. So it's kind of limited, and it's just east of the Antarctic Peninsula. And then looking at the vertical profile from 0 to 2 meters. So this is looking from the 0 to 2 meter depth, what the density is. And what we can see here is that if we look at the point at which we had this intense melt event, there's a densification that kind of persists after a while. And another figure from this paper also shows the way that this limited the liquid water going further into the snowpack. And another way to look at this, or the most important thing in my opinion, is the way that you had this overlying fresh snow in July, which you just didn't have in July of 2016. So by the time you hit the strong melt event here, this was dense enough to potentially hold lakes at the surface in a way that it wasn't in the previous season. So the ultimate goal summary of this is the densification of firn and the associated potential for hydrofracture can be disproportionately affected by intense off-season melt events. And it's important that it be off-season because you don't have the time for the replenishing snow and the replenishment or lack thereof of snowfall. And again, the model was at 7-kilometer resolution, so there were certain difficulties with this. So I'm going to transition now from Fern to lakes and from Antarctica to Greenland. And this might seem a little bit of a huge shift. And this, the work I'm about to talk about is work I've done at NASA Goddard. But the reason this happened is because I happened to be on Operation Ice Bridge over Antarctica for 2 seasons. And at this point, I'd only ever looked at a regional climate model version of Antarctica, but had the opportunity to basically look out the window and see what I expected to be this sort of like, uniform grid. It was instead mountains and lakes and, rivulets, and was obviously like wind erosion. And aboard the aircraft was the Airborne Topographic Mapper, which is a laser altimeter, which is at a 532 nanometers. So they pointed out that there was a potential dual return of the surface and the bottom of the lake. So fortunately, ISAT-2, which is the spaceborne laser altimeter, was coming out in 2018. It was launched in 2018. And so what could be done with the Airborne Topographic Mapper could potentially be done by ISAT-2. And so what we're doing here is using the fact that you have this surface and bottom return coming in from ISAT-2. And once you calculate that depth, using a relationship that was first developed by Box and Ski between the reflectance from imagery and the depth along a specific line to calculate the depth over an entire image. So this is an empirical method that's been developed by many other people in the past. So this has sort of culminated in work that was superglacial-like bathymetry using ISAT-2 and imagery. And my co-conspirator here was Bert Wouters at IMAO and TU Delft. And the two things that were kind of unique about this were the algorithm WADA, which uses ISAT-2 ATL03, and it calculates lake depth and surface at the native ATL03 resolution. But the surface type, and it also assigns surface types based probabilistically. So, based on certain characteristics like surface ice or subsurface ice. And we also use Planet SkySat data and Planet Scope imagery, which I'll talk about in a second, which are very high resolution. And just as an aside, the name WADA, it's actually just our names squished together into a hydrology pun, but it was a lot better than most of the other acronyms we were coming up with. And so this is a paper that is currently in review, and the first version of WADA came out in Fricker et al. And so that's also available now. So I'm going to talk a little bit about the data set here. So over 2019, because I think that ISAT-2 was actually not pointing correctly when it was over Antarctica in 2018, so we waited for the summer of 2019. And obviously we didn't know it was going to be an intense melt season, but we did know that Operation Ice Bridge was going to be running at the beginning around April and then around August over Greenland. So we have this like really rich airborne data set that's about to happen. We have ISAT-2, they were going to plan certain passes so that you had Operation Ice Bridge and ISAT-2 going over the same lines. And so I became a part of the Small Satellite Data Buy program as a PI and tasked a lot of imagery, a lot of really high resolution imagery all over these fast flowing glaciers at these locations. So I'm pointing this out because it's work I'm not doing anymore, but if you want to contact me about this, I think there's still a lot of imagery over this really intense melt season in combination with the Ice Bridge data. So that's potentially really valuable. Oops. One second. Okay, there we go. And just to get a sense of what this, how much more this imagery can show, what we have at the left is Sentinel-2. Sorry, that should be Sentinel-2. And this is a 10 meter resolution. And as you can see, it gives you a lot, but SkySat imagery, which is about a 1 meter resolution, gives you a lot more detail about surface hydrology. So the paper itself used 50 lakes to develop WADA and had 14 lakes with simultaneous ISAT-2 and Planet SkySat imagery. And what we're seeing here is one figure from the paper, and the Ice Bridge line is shown in green. And this was on May 15, 2019. The specific RGTs that were used for ISAT-2 for each of these lakes is shown as well. And some lakes that are described in greater detail. And the letters are, this is Lake Cecily, like I said, these are named for my goddaughters. Lake Niels and Julian, these are named for Barrett's sons. And Lake Zadie, which is named for the author Zadie Smith. And so this is another figure from the paper. And what this is showing is the lake surface and bottom is determined by the WADA algorithm. And in addition, you can see they categorize as the top as being surface ice, and this region right here is being subsurface ice. And the reason that the difference between the black and the blue is because black is associated for correction for refraction. So what this does is once you have this like depth relationship, it develops an empirical equation between reflectance values from these imagery sources. Co-registers it, comes up with the lake boundary and then applies that depth estimate to the entire scene. So here you can see this is from SkySat imagery, and it's giving this really, really crisp detail of the bottom of the lake. Now, this is a time series that was developed from different imagery sources. Now, the IceSat-2 pass, I think, happened on May 23rd. And so what you can see is that, although it comes at different resolutions, this is showing the lake actually being filled in and then draining. And one thing I kind of wanted to point out that I thought was interesting is the way that the Landsat data at 30 meters, you can see the depths are quite similar, but the details are much finer in SkySat. But more importantly, they're also very fine in PlanetScope, which is a 3-meter resolution. And the nice thing about PlanetScope is while SkySat is something that I had to task, PlanetScope data is actually available from Planet regularly, and also it often has multiple passes each day. So this is snapshots before and after the drainage of Lake Julian. And this is where we actually have coincident operation ice bridge imagery and radar and ATM. So this potentially has a lot of information about lake drainage processes. And we can see here is 2 passes, one on May 15th and another on August 14th from IceSat-2. And using the WADA algorithm, it is 0.7 meter resolution, we can see the lake depth here, but we can also capture on August 14th ice layers, potentially ice layers at the bottom, as well as like overall surface lowering. So this is an image from August 20th, and we can kind of point out these sections where we have potential ice layers like along the track. And if we look here, and this is an image from CAMBOT imagery on Operation Ice Bridge, and this is about a 37 meter resolution on May 15th, and this is showing very distinctly the point of where you have stream formation, as well as what is potentially Moulin and this other drainage point. So this is kind of a wealth of potential imagery to think about drainage patterns over Western Greenland. So I think, hold on, I don't understand why I'm having a problem with this. Okay, so that's it. That was the last fun slide. So the future work with WADA is probably going to be over Antarctic ice shelves, depending on what Bear wants to do. But my work currently at University of Colorado Boulder is mostly focusing on snowfall now. And so I'm zooming out to the scale of a global climate model, and that's at about a 1/4 degree resolution. And I've been working with this variable resolution grid, where you have essentially a nested grid inside of a global climate model, which will allow for a lot of experiments examining the impacts and drivers of extreme snowfall, including atmospheric rivers. So thanks, and feel free to contact me. Okay.
Awesome. Thanks so much, Tree. And then again, if you've got questions for Tree, feel free to put them in the chat or just keep them in mind for our question session. So our last talk this morning is by Tom Hudson. Tom's a postdoc in the Department of Earth Sciences at the University of Oxford. His research involves using seismology to study fundamental physical processes at glaciers and other Earth systems like volcanoes. And today, Tom will talk to us about breaking the ice using ice quakes to observe hydrofracture-induced crevassing.
Great stuff. Thanks, Lauren. Can you see and hear me? Yeah.
We can. I'll just pin you really quick. Yeah, I think you're all good. Go ahead.
All good? Great stuff. Thank you. Yeah, thanks for arranging these seminars. They're a really great medium for sharing our science. And yeah, thank you, Lauren, Tavy, and Rebecca, and everyone who's organised them. Yeah, so let's get started. So I'm going to talk today about using ice quakes to observe hydrofracture-induced crevassing. And these are my co-authors. I've kind of worked on this project. So before I go any further, I thought it'd be good to introduce what an ice quake is for those of you who probably haven't heard of them before. Ice quakes are caused, are like earthquakes, but they're caused by the movement or deformation and really fast strain release in ice as it moves. And they can be caused by things like ice flowing over the underlying bedrock, like this outlet glacier in Antarctica. They can also be caused by calving events, such as these icebergs carving off this ice terminus here. And they can be caused by things such as crevassing, and that's what we're going to focus on today. So we're going to focus on these surface crevassing events that are caused by fracture of the ice. So why do we care about crevassing? I guess specifically, why do we care about hydrofracture crevassing? So we care about it for a couple of reasons, and Tree did a great explanation of some of the reasons why we care about it in her talk, actually, and certainly the source of hydrofracture fluids. So one of the reasons we care about it is because these fractures weaken the ice structure, both at the surface and you can often at the bed as well. And these fractures can propagate down, so say a carving front, and then they can preferentially cause more carving of ice than you otherwise would get. And obviously that can enhance sea level rise contributions from this carving. You can also have superglacial lakes forming on the ice surface, and then these crevasses can provide pathways for water to get down to the bed if they can get into a crack and promote hydrofracture. And these are common processes that are mainly observed in Greenland. In Antarctica, we mainly observe hydrofracture, it's probably fair to say, on ice shelves, or at least that's where the biggest vulnerabilities we think are at the moment. The Larsen B ice shelf is a very good example of this, where it disintegrated in 2002, 2003, due to these lakes forming and flowing into these cracks and causing disintegration of the ice shelf. So they can cause massive catastrophic instabilities in ice sheets and ice shelves. Just to put some numbers to this, here's a couple of studies that caught my eye as I started this work. There's a Pollard et al. 2015 paper, which suggests that hydrofracturing and ice cliff failure can cause of the order of 17 meters of sea level rise within a few thousand years. And then, which is quite a lot, obviously. And then there's a great paper out in Nature in 2019, it's just over a year ago, showing the vulnerability of Antarctica's ice shelves to meltwater-driven fracture. And if you can see this map here, you can see these red regions are the regions that are vulnerable to hydrofracture. And basically the story is pretty much all the ice shelves in Antarctica are vulnerable. So it's an important process that could cause significant loss of ice off the Antarctic continent and off Greenland. So what is hydraulic force crevassing? How does it work, and what are we observing here? So contrary to popular belief, maybe from children, fractures are not caused by squirrels or whatever this animal is putting acorns in the ice. They're caused by a stress regime at the surface, preferentially causing cracks to open. But ordinarily, if you have this stress regime, it is compensated by the ice overburden pressure. So as you get deeper into the ice, the crack wants to close more and more until the ice overburden pressure overcomes that preferential tensile stress field and closes the crack. So you can't get a crack propagating any further than what we call this maximum dry crevasse depth, or this green line I've drawn on here. However, if you have water present in a crack, you can then get much deeper, and actually you can get all the way to the bed because the water is denser than the ice. And so the hydrostatic head of the water, if it's, say, the cracks filled to the surface, can provide sufficient pressure to propagate all the way to the bed in an unstable fashion, and obviously get to the base of an ice shelf or get to the bed of an ice sheet, lubricating it and accelerating it into the ocean, as Tree talked about earlier. So what we do is we use an argument. Well, we want to decipher first whether our ice quakes are caused by hydrofracture or just dry crevassing. And to do that, we have to have two pieces of information: the ice quake depth and the maximum dry crevasse depth. To get the maximum dry crevasse depth, what we do is we do quite a simple first pass at this, and we take the ice surface velocity from GPS data, and we obtain a surface stress field from that, and then we calculate a maximum dry crevasse depth. I won't go into the maths behind this, but it's not terribly complicated. But what we get out is we get out a sort of 2D field of maximum dry crevasse depth, which we can compare our ice quake depths to. To get our ice quake depths is a little bit more complicated. Ordinarily, we would, to get an earthquake depth out, we would look at body waves. So we look at P and S waves for a normal earthquake and do a kind of triangulation to work out where the location of the, or that hypercenter of the event is. However, for crevassing events, we're often very, very shallow and very close to the surface. And our station spacing is normally, or seismometer spacing is normally insufficient to really resolve ice quake depths in that way. So what we do is we actually use P waves and what are called Rayleigh waves. Rayleigh waves are a bit like ocean waves. They're surface waves that travel on the surface of the ice. And we use an amplitude ratio to get out the depth. Don't worry, you don't need to know any more than that. But if you're a seismologist, feel free to ask me at the end if you want to know more details on that method. Oh, sorry. And so what we can do is we can then kind of form a simple hypothesis or kind of test to see whether an ice quake is caused by hydrofracture or not. If an ice quake is above or shallower than the maximum dry crevasse depth, then we suggest that the mechanism is inconclusive. It could be caused by hydrofracture, but it could equally be caused by dry crevassing, as I'll call it. If the ice quake is deeper than this maximum dry crevasse depth, taking into account the uncertainties, then the ice quake must be hydrofracture. There's no other way you could have a fracture mechanism if it is crevassing, a fracture mechanism that deep. And this is the argument we use to decipher between hydrofracture and non-hydrofracture ice quakes. To study this process, we've gone to Vatnajökull in Iceland, in southeast Iceland, and specifically Skeiðarárjökull. Apologies for any Icelanders in the audience who I've just ruined your language, but this is an outlet glacier which is moving at about 60 meters per year. And our study site is here. And it's a great place to study hydrofracture because Iceland is basically very wet. If you've ever been there, it's probably been raining when you've been there. And we studied this site, we went to this site in June in 2014. And so there's a lot of water present at that time of year. So it's very good conditions for hydrofracture. So on to the results. I'm going to take you through 3 key results from what we've observed in this data so far. We've observed thousands of crevassing events in our ice quake data set. And they're all shown by these green dots here. But I'm just going to concentrate on 6 of these ice quakes shown here with their source mechanisms. I'll talk about what these source mechanisms mean in a minute. And the principal stress directions, which are these orange lines, which I'll talk about again in a minute. But we just took these 6 events because we need really high signal to noise ratios to do some of this analysis that we've done and really interrogate the quantify what's going on in these processes. So yeah, so we've just looked at 6 events here. The first important result to take away is the depths of the ice quakes, right? Because that's saying whether or not these ice quakes are associated with hydrofracture. If we zoom in a bit, I can't see one of my ice quakes, but the ice quake I can't see is the most critical one, which is over here on the right. And that ice quake is deeper than this maximum dry crevasse depth. The maximum dry crevasse depth is shown by this solid red line here, with dashed lines being uncertainties associated with that. And that ice quake is deeper than that maximum dry crevasse depth within the uncertainty. The other ice quakes are also deeper, but obviously their uncertainties overlap this line a lot more. So I think the important result we can take away from this is that we think we do observe hydrofracture at least once out of these ice quakes. But obviously this is just the first pass and it's a bit tentative. But I'll show you what we can do with it if we assume that this event is caused by hydrofracture. So we can then look at the source mechanisms. And an earthquake source mechanism describes the physics of how an earthquake fails. So it describes kind of how the stress or the strain is released during an earthquake. And an important thing to know about source mechanisms is you can plot them up on these loom plots and work out what kind of failure is exhibited by the ice quake. I'll briefly take you through what these mean because they can be a bit complicated. In the center here, if we had an earthquake plotted at the center of this loom plot, that would suggest it was what we call a double couple event. That's just like a tectonic event you might have, between 2 plates sliding in a tectonic sense, maybe, I don't know, at the San Andreas Fault in California, for example. Then you can have explosions or implosions. An explosion example might be like a nuclear bomb test, or an implosion might be a mine collapse. And then you can have cracks. And these are obviously what we expect crevassing to be. And you can have opening cracks, which lie somewhere around here on the loom plot, and closing cracks, which lie down here. So here are 2 of our ice quakes. And the important thing to note is that this star represents the most likely solution, but the PDF of the solution is represented in this color. So this isn't a terribly well constrained event, but it is lying somewhere near a tensile crack event. And the orientation of this crack actually matches really well. It's kind of a north-northeast kind of fault, and it matches really well with our principal stress directions, which are indicated here by these orange lines. If we then look at this event, this event shows potentially a closing event, although I point you to the loon plot and show you it looks like it's a closing crack, but actually we've got quite a significant section of the PDF up in an opening crack. So it's actually a fairly poorly constrained event, and this could be an opening or closing crack. It's obviously difficult to conceive of a closing crack, but I'll talk briefly at the end in one of my last slides about what could cause a closing crack crevasse. So that's our second important result, that we observe crevasse opening and possibly closing in the expected orientation of the stress field. So finally, onto the final important result, I think from our analysis so far of these events, and that is that we can start to quantify some of the physical parameters associated with this ice quake source. And I'm just going to show you one here, and that's the amount of fluid that's opening this event. So if we look at the magnitude or the size of this earthquake, we can calculate the magnitude of the volume of fluid injected into this, to open this crack up. And we find this is about 1.6 meters, 1.6 times 10 to the minus 2 meters cubed. Obviously, that's not really, I can't really imagine how much volume that is, but that's about 1/10 of your bathtub. So it's really not that much water, which is actually, I think it's quite impressive that we can really observe that kind of mechanism or that kind of fluid movement in a glacier. So if we just put it all together, there are two mechanisms for opening cracks that we kind of conceive of and suggest in our paper we've recently published on this. The first is that we're opening new cracks. The second is that we're opening pre-existing cracks. And we can't really decipher between either of these. It's very difficult to discriminate between either of them because they're both opening crack mechanisms. Now I mentioned that closing crack mechanism. And if we look at this, this closing crack, the only way I can conceive of a closing crack occurring at the moment, and I'm not even sure whether this is conceivable in reality, is if you had a pre-existing crack with no fluid in it, and then if you had fluid flows through a crack and then opens up at a section of the crack and then flows out and is evacuated sufficiently quickly that that crack closes seismically, i.e. sufficiently quick timescales to have elastic kind of failure. And that seems unlikely to me, but I kind of put it in for completeness. So I reckon mechanisms 1 and 2 are what we're probably observing predominantly. So I just thought I'd finish really with highlighting the implications. So I guess the first implication is these are the first direct observations of a hydrofracture mechanism, actually observing an individual fracture event, which I think is quite exciting, at least for me as a seismologist. The second implication is that ice quakes could be used to study the mechanisms, and quantify the physics going on at that fracture at that moment in time, the pathway of this melt water through these cracks and potentially to the bed, and the extent of hydrofracture. So you can kind of quantify how many ice quakes are occurring and sort of put together a fracture density of the ice. And this work's kind of opens up some questions, or I guess these questions are open questions that are already there. But one question is, how can increased knowledge of this mechanism, this physical mechanism, help inform ice sheet stability? And a second question would be, how can we assess the extent and therefore the risk posed by hydrofracture to Earth's ice sheets in their current state? So to conclude, we've shown that we can observe ice quakes associated with hydrofracture, or at least we think we can. We can invert for source mechanisms, and we can quantify the physical hydrofracture process. And obviously this has significant implications for both ice sheets and ice shelves, such as the Larsen B ice collapse 2 decades ago. So thank you for listening. If you want to find out more, we've just had a paper published on this, so you can dive into that if you're really excited about it. And also, if you're a seismologist in the audience, I try to make all my code freely available. So if you want to try this out on your own data sets, feel free to just take and use my code. So thank you for listening. I've also been asked to advertise the talk for next week before we go into questions. And that is titled "From Ice to Coasts, Connecting Our Science with Coastal Communities." And Robin Bell from Le Mont Dirty Earth Rajashree is going to give that talk next week. So tune in to that if you're interested. yeah, thank you for this opportunity to speak.
Awesome. Thanks so much, Tom, and to all three of our speakers. So if you've got a question, maybe feel free to either put it in the chat or just note in the chat that you have a question, and then we can get through them all. So it looks like Roger, if you'd like to unmute yourself and ask, go ahead.
Yes, thanks very much, Tom. And apologies to the first two speakers. My Zoom was playing up and I missed your talks, but I'll watch them on YouTube. Tom, thanks very much. Enjoyed that. Just wondering how you managed to put the uncertainty bounds on the Peter Rayleigh depths. Inevitable with real data. And is there an uncertainty that you could offer for the maximum dry crevasse depth, just to be doubly sure that the ones you're looking at are really hydrofracture? Thanks very much.
Yeah, that's a great question. So I kind of present that we've seen hydrofracture tentatively in a way because as you say, the uncertainties are really large. Peter Rayleigh wave amplitude ratios, I won't bring up the plot again because it'll just take too long, but they have significant uncertainties themselves. The way we calculated the uncertainties with those is we took the P wave amplitude and then we looked at the background noise for a second before the event. And we did the same with the Rayleigh wave, but obviously use the same noise because you can't use the noise just before the Rayleigh wave because you've got an S wave arriving or a P wave, depending on your source. We did also calculate uncertainties in the maximum dry crevasse depth. They again are pretty large. They're of the order, maximum dry crevasse depths of the order of sort of 25 to 50 meters, and the error is of that order as well. It's of the order of 25 meters or so. And that error is mainly caused by the GPS data. We use the GPS data actually from the seismometers themselves, and obviously doing that, they're not dual band frequency GPS units, so they're single band, so they've got quite a lot of uncertainty associated with them. So I guess we're really pushing the boundaries here. I'd really like to go back with decent GPS instruments and more seismometers, and then you can constrain all those uncertainties. Sorry, that was quite a long answer, but I hope that answers your question.
No, really interesting. Thanks very much.
Great, thanks so much. Does anyone else have a question for any of our three speakers?
I have a question for you, Tree. Is that allowed?
Oh, absolutely. Go for it.
Fantastic. Yeah, thanks for a great talk. I'm really intrigued by this. I hadn't thought about it before, but obviously it's kind of obvious when you think about it. But in terms of this densification of the firn due to, say, melt events periodically, as well as being able to support superglacial lakes better, do you think that has implications as well for hydrofracture? Because I guess it must wipe out any signature of crevassing potentially, or it could like weld these crevasses back together.
Well, there's so the densification. The better way to think about it is that the densification is more likely to make fractures on the surface occur at all. But there's also I would refer actually to Bell 2018, I think it is, talking about the way that surface hydrology can potentially take water away. So you build this dense firm layer that can support meltwater, but then you also have these lakes which can potentially route meltwater away, so that that can protect in some sense the firm layer. So it's a weird balance between what actually goes on the surface versus what gets left in the firn. But yeah, it's complicated. So I mean, I guess my answer is I'm not sure I can directly say that it's necessarily the case that densification will automatically mitigate against hydrofracture. And I actually had a question for you. Sorry, I'm okay with this. You showed a figure where you had the closing that you had the fracture closing with water underneath. And I'm sorry, I can't remember exactly the details, but right. So how common is that? Does that change the stress regime? So if you were from the perspective of a crevasse that closed at the bottom, and then there was another crevasse below that contained water, does that make a difference to the stress regime?
So if you had water below a crack and then it somehow got isolated and then
exactly
more water coming down,
Does it matter that there's a little pocket of water underneath, or is that?
Yeah, I guess that would change the stress regime. Yeah, because there wouldn't be. I guess that water would want to carry on down because it would have a greater. Well, but it wouldn't have necessarily. It'd become quite a complex problem because I guess it depends how much water you've got as to how unstable it would be, I guess. But I guess it could sit there stably. That's the right word. Yeah, that would obviously affect that obviously could affect the pressure that could drive the fluid through. I would really caveat to everyone in the audience. I'm not suggesting that we can necessarily have these closing cracks. It's really difficult to conceive of these cracks closing on sufficiently quick timescales to emit seismic energy. That's the only method I could really conceive of it doing it. So I guess when we start to dive into thinking more about is the water below it, again, we're looking into more of a potentially an imaginary realm. But yeah, it's a great question. It certainly would have an effect if it could happen.
Right, but it's kind of turtles all the way down. If you have more meltwater than we can see, there's just an entire stress regime that we might not be accounting for. I guess that's why I'm curious. It never occurred to me that you would have little pockets of water underneath a crevasse like that.
Yeah, exactly. That's a great question. Who knows? There might be pockets of water in there.
Yeah, that's good.
Awesome. Any other questions? Feel free to just unmute yourself. Yeah, Paco, go ahead.
Hello. Nice talks, all of them. I have a question for Denis. In particular, some of your slides, to me, seem to suggest that the sliding law, the choice of the sliding law, could be the reason for the largest difference in the mass change. For instance, the one before last, so you see the oscillations, you see the bias and so on, but really you have in the one before last, I think there was a big difference just because of the sliding law in terms of mass change. You have mentioned that the bed slope had a bigger effect than the choice of the sliding law, but I didn't catch, maybe I missed some slide explaining this.
No, that's a good question. I think the answer depends on how you choose to interpret what it means to be a bigger or smaller effect. When we looked at the bias as a percentage of the total loss. So in other words, all of the glacier simulations go through some mass loss. And when you take up the bias as a percentage of that total mass loss, the bed played a bigger role. In other words, if you change the sliding law, it was approximately the same percentage. The bias was the same percentage of the total loss. And the two different bed slopes were a different percentage of the loss. Now, if you look at, now you're totally right, and you didn't miss a slide, and that was a little unclear in the way I presented it, is that if you look at the magnitude, the total magnitude of the bias, the sliding law does play a role. So it depends on how you frame it. And the reason we looked at the percentage is because when we were thinking, okay, how do we scale up this one idealized outlet glacier to the entire ice sheet or a group of glaciers, we thought that the bias as a percentage of the total change of a region or an ice sheet would give us more information. But you're right that the magnitude does depend on the sliding law.
Okay,
just like the magnitude of overall mass change depends greatly on the sliding law too.
Yeah. Okay, thanks.
Great, thanks so much. We're at the end of the hour. Are there any final questions for any of the three speakers?
I think, Tom, Roger asked if you can put your new paper reference into the chat. And just to say what there is on Facebook, there's lots of thank you. And Doug did comment and say, thank goodness for the squirrel. He teaches us glaciology. And he also said, just in case you're not reading the messages on Facebook, that this is about trees talk. This is fascinating, mesoscale. Föhn winds have a huge impact on the ice surface at wide scale glaciological speaking. Nice talk.
Awesome. Neat. So with that, maybe we'll thank our three speakers again. Thanks so much, all three of you, for joining us.
Thank you.
Yeah, and see everyone next week.
See you all next week.
Okay, bye.
Bye, thanks.
Have a good weekend. It's coming up.
Oh yeah.
Right, so.